So we see that we have what's called the wave-particle duality. Again, light behaves sometimes like a particle, sometimes like a wave, and electrons too act sometimes like particles and sometimes like waves. And this would apply to the neutrons and protons as well. And so this is a strange phenomena that we see based on the kind of experiment we're doing, that these will behave either as particles or as waves. Max Planck suggested that light was made up of packets of energy again, and this was his formula. The value for that h we were talking about earlier, Planck's constant, is this really tiny number. And so you see that energy comes in really tiny packets as well. Einstein, of course, showed that these had also come in little packets of energy, that energy was not continuous, and things are more discrete and granular in nature. And the photoelectric effect is really what made Einstein famous. Unfortunately, at that time, his E equals mc squared was not understood by many people. It only became clear to them after he passed away. And so he never got a Nobel Prize for the E equals mc squared, but he did get it for the photoelectric effect, which was one of his, not so important discoveries compared to the theory of special relativity and general relativity. So let's look at this photoelectric effect some more. We see that light photons are falling on this metal, sodium, and electrons are being ejected from the surface. And it turns out that one photon can only eject one electron. That's the rule. If you have more than the energy the electron needs, it's going to come out with more kinetic energy, but it uses only that much energy that you put in. So now, if I have a material like this and I shoot it with light, if there's not enough energy, then the electrons won't get emitted. But if there is enough energy, it will. So if I try, say, red light, which has low energy, I can go ahead and put as much red light. And if you guys follow this with the PowerPoint, the presentation, you'll kind of see the animation here. And you'll find that when you put red light, doesn't matter how much red light you put in, you could send in one photon or you could send in 20 photons, nothing gets emitted because there's just not enough energy for that electron to be able to grab it and jump out of its orbit. It needs a certain amount of energy to get out, like an activation energy. Unless it doesn't get it, it doesn't emit. So we see that red light has a lower energy than blue light. So if we wanted to get that to do that, we'd have to increase the frequency of the light, not the number of molecule or particles of light, but rather the frequency, the energy of each individual photon. So here we see we apply, even send three of them together, still nothing gets things. So you say maybe it's not bright enough. Let's make it more bright, make it more intense, and you put more of the red thing, so it becomes a brighter red thing. But still, nothing happens. No electrons get emitted. And I suggest if you guys do this, do it through the screen, the mode where you view the PowerPoint, in a presentation mode, and then you'll be able to see that little animation with that thing going on. Now we try it with blue light, and that's going to have enough energy, and these three photons will emit three electrons. And more blue light means more electrons. That means that it is accepting them. So all of these guys, you got 3, 4, 5, 6, 7, 8, 9 photons that emit 9 electrons. Each of them will get absorbed. And so we see that it is the frequency of the light that makes it happen and not the intensity. That's the key thing I want you guys to understand. There's a certain cutoff frequency. So for every metal, it'll have a certain amount of energy it needs to be able to eject that electron. And if the photon has that much energy, then it will be ejected. Otherwise, it'll just bounce off and none of it will get absorbed. And so Einstein, of course,